And the final section of this talk is on data in the cloud. And we discussed different ways you can look at data in the cloud. And we have clouds have this sort of unique processing model, MapReduce with Hadoop, which we've discussed. But they've also inspired a revolution in data models from the so-called NoSQL approach to data, which is aimed at data which is less structured than databases. Databases have these fixed schemas, and you generate tables. The tables have properties or features, and every record in the table has the same properties / features. Whereas in NoSQL, you have a more flexible model, and of course there's a cost there. Because you have more flexibility, it actually makes it easier to scale because you're not so fixed, but also it means you're less efficient. And so databases, when they work, are probably your favorite. By databases, I mean SQL databases. They're going to probably be your best solution. Another important feature that is necessary is the size, namely one often wants to access large chunks of data which tend to be not so useful for SQL, and you need to use lots of custom software. If you look at this Large Hadron Collider, there was a time people looked at so-called object-oriented databases, but found it was actually better just to read things from files and put your capability into user software. Actually, object-oriented user software, C++, but that was a better model than actually putting all the intelligence into the database. So a lot of what's done here is you have relatively bland data storage systems with rather modest capabilities, but because of that, highly scalable and huge intelligence in what sometimes is called the business logic, the actual code that processes the data. So we have different formats for data. We have traditional Windows and Unix file system arranged hierarchically. Those can be accessed online through systems like OnCourse at Indiana University, that's Sakai, Dropbox, or Windows SharePoint, Microsoft SharePoint. And they had often access with standard Unix I/O commands or via the web. There's other systems. We have what I call data parallel file systems, which are like the Google file system originally, or the Cosmos from Microsoft. And then we have the Apache Hadoop file system, where we have files split up so that each part of the file lives on a particular computer, and you hope to use that computer to process that part of the file. They also have replication for fault tolerance. Then we have object stores like Amazon S3 or Azure Blobs, which are designed to scale and have a simpler interface than traditional file systems. We could discuss databases here, but on the later slide, not the next slide, we'll discuss them as a management system. Now let's think about clouds as support for data repository. We have the data deluge. We need to find lots of cost-effective computing. Clouds are by definition the cheapest form of computing because they have the best data center technology and they get economy of scale. But then what do we do about where the data is? Because the data may not be on the cloud. And so that's not so trivial. If I'm Google, I can arrange that my cloud has the data where the computer is, because I built my computer to process my data, and that's no problem. However, if I'm a scientist, I need some genomic data one day, some environmental data the next day. Quite how I reconcile that and get all that data in the same place is not so trivial, especially when I need to share resources to be cost effective, because we really don't want to have every scientist storing their data and downloading their petabytes either to their personal cluster or to their university cluster. So we need to reconcile the distributed, which is the initial source of the data, with the shared analysis. We could move data to disciplinary specific clouds, but I gave the example of genomics and environmental data. It's not so obvious that those clouds The genomic cloud will not store its data in the same place as the environmental cloud. And that's what I said, how you deal with multidisciplinary studies. We can expect that the data repositories of the future, currently they're just bunches of disks, but you can expect them to have cheap data and elastic cloud support in the future. There was a suggestion in the meeting I went to recently that data would be supported free or hosted free if you could be used commercially. So the model was that storage was free and you paid for your computing. So we can imagine changing the we imagine changing the model. Previously, we had things like EOS, DIS, Earth observation, GenBack for genomics, NSIDC for polar science, IPAC for infrared astronomy, the LHC, OSG computing grids. These are repositories optimized for a particular field. The LHC one is highly distributed. The other ones are probably more centralized. But now we come to the data deluge. It's probably a good idea to rethink this model because of this difficulty of whether we can bring the computing to the data or whether the data is going to end up in the wrong place, or in that wrong place is either because it has a cloud attached to it and can do some computing, or I want to use that data with other data which is living in a different cloud. Then we need to look at the file system. Here's a sort of traditional high-performance computing file system. We sort of 3 levels: an archive, a storage system, and then a cluster. And then we can have multiple clusters here, and they all share this file system. And that file system is all backed up on the same archive. This is where technology like network file systems and Lustre come along. The disadvantage of this approach is it's highly effective. It's generalized things like GFFS to distribute it across the country, but it doesn't bring the computing to the data. And we can replace the Unix-style Unix Lustre file system with object stores, and they have actually a relatively similar in concept. And we have a separate storage set of nodes from the compute nodes. In the data file system, this is HDFS or GFS. We have a file, we break it up into blocks. A given block gets stored on multiple computers for this replication both supports fault tolerance and also performance tolerance, because if it's say stored here and here, I can choose which of those computers to use to process that data, depending on which of those computers is less used. And this doesn't necessarily need any archival storage, and we can imagine the computing being brought to the data because every data store has a compute node attached to it. So when we come to managing the data, this is what following up on the previous slide. On top of the format, we need to manage it. We already mentioned the directory structure, and actually we can manage data by just using the name of the file. I'm sure all of you have done that a little bit on your PC or Mac. And we can also use things like iRods as add-on metadata stores to manage this. And the contents of the file itself can be self-managed with XML. Of course, we can also use databases, which are a very effective way if your data is presented as tables, and that database can have indices for very fast access. Then we have these newer NoSQL approaches we sketched before: HBase, Dynamo, Cassandra, MongoDB, CouchDB, React, Amazon SimpleDB, and Azure Table, this type of system on the public cloud. And HBase is built on HDFS, and they store entities in distributed, scalable fashion. There's no fixed schema, and these are meant to be data center or web scale storage. And these tend to be so-called document stores or column stores, depending on how you get parallelism from their decomposition. Often these systems here are linked to a dupe to do the actual processing. So that's the end of our discussion of clouds. We gave a lot of gossip about, which should by now you should know what a cloud is. And then we discussed a little more precisely how data is stored in the cloud. And this is all an immature technology changing rapidly, but it is bound to be important. And we just need to watch this space to see how it improves. I thank you again for coming to this class. This is Jeffrey Fox signing off.